In this video, we are going to take a look at switch network technologies. Now, when it comes to LAN switching, there's several different aspects of LAN switching that we really have to understand to fully be able to understand the basically encompass everything there is to it. Now, you might ask yourself, why do I care? This is a service provider series. Why does that matter to me? Well, that's a good point. This is a service provider series, but at the same point in time, um, service providers aren't completely automated. They're not autonomous, which means that they don't build themselves. It takes people to put them together. So you're going to have people that are going to work internally. I work for a service provider. I work from home most of the time, but I'm able to connect in and spin customers up and things like that. Well, the same thing happens with real other service providers. They have people that work internally. They have local area networks. They have internal routing. A lot of times, service providers will have two sets of engineers. You'll have the internal engineering team and you'll have the external engineering team. The external engineering team is going to be connecting customers to the network, whether it's allowing the customer to utilize the service provider's network as transit, so get from the customer's location to, say, Google or INE.com. Other customers may need to utilize services that the service provider offers, whether it's cloud storage, whether it's email, hosted web, whatever it might be. So there is a very in-depth need for this. So it's important to understand both the wired connection and understanding the internals and stuff like that. And this section is going to cover that in a lot of detail. So when we first get into it, we're going to basically break down understanding what Ethernet is. We're going to take a look at connecting to an Ethernet LAN, what the switch LAN technologies are, operating a Cisco switch, switch security, switch network optimizations, and then we'll go from there. Now, when it comes to understanding Ethernet, there's quite a few things you really need to understand. First of all, we're going to define what a LAN itself is, because if you don't know what LAN, LAN, or local area network means, you may have a hard time getting over that little hump. So once you understand what that means, you can move on to the next set of definitions. We'll take a look at describing the components of a local area network. What makes up the LAN? If you were to hear someone talking like a network engineer, maybe you're coming from the system side, or you don't know much about something and you're wanting to know more about it. If you hear the network team talking and they're talking about, layer 2 issues in the network, if you know more about layer 2, you might be able to say, okay, well, maybe they have a duplex mismatch, maybe there's a CDP issue somewhere, stuff like that. We'll describe the functions of provided by a LAN. What can you do when you have the network? Whether you're at home, whether you're at a mall, or whether you're in an airport, those are all local area networks. The local area network doesn't necessarily mean the physical cabling connections that you connect to. If you go to a school, some universities are known as a local area network. But a LAN could be the entire campus, 20, 30 buildings. For instance, if you go to Cisco's locations in RTP, where I took my CCNA lab, or you go to San Jose, California, the funny thing about it is you walk in and you drive through the Cisco campuses, they're massive. That's one big LAN. But they're subdivided into multiple sub-LANs, and we'll talk about that in more detail later. Describe various types of and sizes of LANs, which, again, goes back to, a campus can be considered a LAN, a classroom can be considered a LAN. Let's break down exactly what that means. Describe the evolution of Ethernet and identify standards for Ethernet LANs. We'll take a look at describing LANs using CSMA CD, or Carrier Sense Multi-Access Collision Detection. Describe the format of an Ethernet frame and describe how the MAC address is formatted in an Ethernet LAN. So, without any further ado, a LAN definition. A LAN is a network of computers and other components located relatively close together. Now, the nice thing about that is it doesn't necessarily mean that, my LAN. The funny thing about that is LAN is kind of a relative term, and what I mean by that is you could theoretically consider a LAN something that you can reach even over a WAN. So I'm going to go hit say I have a site in Chicago, I have a site in Milwaukee. Well, technically they're not physically connected. They're not even remotely close to each other. Probably about 100 miles away. Well, that's great, but if you have a site-to-site VPN, if you have a MPLS Layer 3 VPN, if you have some sort of WAN connection between them, then you can be in Chicago and access resources in Milwaukee. Very cool. So basically, LAN describes something that is physically close to each other, but it could be relatively far away as well. Now, LAN components. Well, you got computers and PCs, servers, things like that. You have your interconnections. You have your network interface cards and your media. So your NICs are going to connect the internet or the cable, whether it's fiber or whether it's Ethernet, to the computer. That's what terminates the actual cable. You have network devices such as hubs and switches. Also routers, access points, repeaters. Those are all devices that could potentially be a network device. You have protocols, Ethernet, IP, ARP, DHCP. Ethernet, IP, ARP, and DHCP are all examples of routed protocols. Now, what's the difference between routed and routing? Well, a routed protocol is going to utilize the streets, the roads that are built by the routing protocols. What are the routing protocols? Those are your dynamic routing protocols: RIP, EIGRP, OSPF, ISIS, BGP, MPLS, VPN. Those are all going to be routing protocols. And some might argue, well, MPLS technically isn't a routing protocol. And I would agree, but it provides you transport from one place to another, so it's routing traffic for you. But there's multiple pieces that go into MPLS VPN, and that's outside of the scope for this particular series. When we get into part 2 coming up, we will definitely take a look at that in more detail, exactly how MPLS VPN works and stuff like that. But for the most part, that is some of the protocols that you can see. Just understand that routed protocols are handling the actual encapsulation, how traffic is handled internally in the LAN, and getting from point A to point B. The routing protocols build the roads and build the connections that the routed protocols ride over. Now, some of the LAN functions: data and applications, sharing files and applications, more efficient collaboration. For those of you that are older, and older I mean 40, 50, 60 years old, you will have the appreciation of what they call SneakerNet. Now, I'm younger than you, but that's okay. But I appreciate the fact that back in the day, early 80s, 90s time frame, there was a thing known as SneakerNet, and that's just a colloquial term for having to carry like a disk. If you want to install an operating system, you would physically have to walk that operating system from computer to computer to computer. There was no way to mass deploy an operating system across the LAN. That didn't exist back then. So as things came along, and the LAN itself evolved, so did for instance, if you want to mass deploy an operating system, I believe it was Microsoft's SMS server, which was eventually replaced by SCCM, or Configuration Manager. Those technologies allow you to mass deploy operating systems over the LAN, but they can choke the LAN out too by too much traffic, and that's a little outside of scope as well. A lot of times those technologies like mass deploying operating systems utilize a technology known as multicast, or one-to-many. And again, that's outside of the scope, but basically it's you're sending one stream of data out, and the network devices themselves replicate that to whoever's asking for it. Shared resources, cameras and printers. But I don't know about you, but everybody that I know has a printer, and sometimes it's networked, sometimes it's not. There's a friend of mine who has a printer in every house, or in every room of his house. And I said, why didn't you just network that together over the wireless? And he goes, because I'm not you. I'm like, oh, okay. But I showed him how to do it, and his wife wasn't very happy with them that they spent $400 on printers, but that was okay. But it shows you that you can utilize the network to give access to resources that may not be physically next to or readily available for the computer you're sitting at. The printer actually sits in my office, but if I go downstairs and say my oldest son is on the laptop and he's got to print a report for school, he can simply pull up the printer, and then he can send it to where it's going to go, send the print job, and it prints up here. It comes through the wireless, hits my computer accesses the print server. It gets done. The point is it's reachable. Same thing with the camera. I have an IP camera to see traffic when I'm outside. I can reach that from the internet. I can reach that from my internal LAN. It's a resource that's available on my network. Communications to other parts of the network. So if you want to get to access to the internet, great. Plug it in, go ahead. Access to the internet is going to be a great location. A lot of times you're going to be utilizing the internet for more than just access to Google or INE or Facebook or whatever you're trying to look it up. Or if you're like me, your pop-up page, it happens to be Cisco's documentation site. So it does play into that hand as well. You could also utilize the internet to access resources that are not close by. So like for instance, there's a technology known as DMVPN or Dynamic Multipoint VPN that utilizes the internet to get customer site A and customer site B to talk to each other. And it's provider independent, which means you don't have to have MPLS in the middle. A lot of customers like that. When it comes to LAN sizes, you have your SOHO, small office, home office, which is what I have here at home, which most people, if you're watching this video, you probably have a SOHO as well. Then you also have the enterprise environment, which may include many LANs, one or more buildings, or corporate campus. So again, it could be, you could have like the college campus that I attended here in the area that I live in. I think there's 4 or 5 buildings, all interconnected through fiber optic cabling. When I first started going to that school, I didn't have a CCNA. Once I achieved my CCNP, I actually worked with their network department because I was a consultant at that point in time, and I helped them build out their environment. And the irony of it is now I go back there as a CCIE, and I teach classes at that school and explain to them how the network is put together and break it down so they're able to see from a large scale. Because a lot of people, when they're coming into networking, they don't realize the scale at how big networks can be. And you start taking things like info blocks, and you start breaking things down into different subnets, and you're able to say, okay, this /27 network is going to go to this particular classroom. And in the school that I attended, every one of the rooms was a dedicated network, because you wanted to have room 202 was separate from room 203. So you would do, 10 was the base network, and you have floor 1 was, 10.1, floor 2 was 10.2, floor 3 was 10.3. And you would go around and you would segment it off. And the irony of it was we used a lot of VRFs. And a VRF, if you're familiar with VLANs on a switch, which if you're not, that's fine. VLANs help segment or basically split up a layer 2 switch into multiple layer 2 broadcast domains. Well, a VRF does the same thing on a router. It allows you to have separate routing tables on the router, virtual routing and forwarding instances. So a VLAN is a layer 2 multiplexing capability of a switch. A VRF is a layer 3 multiplexing of a router. So very cool stuff. We'll talk about that in more detail later. And it's actually a little outside of the scope here, but as you get into CCNA for part 2, we'll talk about that more in detail, because once you get into MPLS VPN and trying to separate customer A from customer B, that's one way to do that. And actually, the school that I attended, they utilize VRFs for, they have a VRF for faculty, they have a VRF for students, and they have a VRF for guests. And they have different networks that traverse through that, and it's kind of complicated to explain it without diagramming it out and stuff like that. But the general idea behind it is here, even with having the 10 network, they wouldn't have enough address space for all the classrooms that they have and all the different floors. So they have to go in and they have to VRF things out so that they have that scalability capability built in, so they'd be able to get the network to grow to the level that they need it to without having to buy extra gear. And then that's the general idea behind it. Now, some of the LAN standards that are out there, you have LLC, which is the Logical Link Controller. This is transitions up to the network layer. Tells the data link layer what to do with the packet when it receives a frame. And that is the first one, the bottom half, and that's why I put them logically LLC on top of the MAC. The MAC is going to be what connects to the physical media and brings it in. So there's 2 different layers to the MAC, the layer 2. Since we've already talked about OSI, there's 2 different layers to the data link layer. You have the bottom half, which is the MAC. You have the upper layer, which is the LLC. So the MAC handles all the layer 2 aspects of it, and then it looks at the ether type value. The ether type value is a section of the Ethernet frame that indicates what that type of packet is. So you're trying to, at the very end of every layer, try to tell the upper layer. So in this case here, layer 2, is using the ether type value to tell layer 3 what it can expect. Then when you get to layer 3, you're looking at other factors and stuff like that. You're looking at port numbers, and you're looking at trying to tell the layer 4 what type of traffic is it. Is it port 80? Is it web? Is it email? Is it SSH? Is it, SMP or SNMP? You're trying to always tell the layer ahead of you or above you what you're dealing with and what they can expect to see. So it's a signaling technology that's built into the framing. So MAC comes in, and then when you're dealing with routing protocols, the layer 2 header is ripped off on a per connection basis. So if you're going from subnet 1 to subnet 2 to subnet 3, the layer 2 header is ripped off on a per routed layer 3 connection basis. So if you're going from 10.1.1.0/24 to 10.1.2.0/24, you're ripping off the layer 2 header that comes in from the 10.1.1.0/24 network, and you're rebuilding it when the traffic leaves that router going out to the next hop. The reason for that is because the MAC addresses have changed, and the source and destination MACs are different now. So then you're going to go ahead and rip that off. You're going to rebuild it with the new source and destination MAC address table and the information it's learned, and you're going to forward that traffic on to the next hop. So that's what the layer 2 header does. The LLC signals up, what do I need to do with this? Is it an IP packet? If so, how do I handle that? And then what the device will do is it will go in there, and the device, regardless if it's a layer 2 switch, a layer 3 router, or a firewall, what they'll do is they'll receive that layer 2 frame in, they'll analyze and say, okay, what's your destination MAC address? Okay, the MAC address is pointing towards me, so I take that in, I rip the layer 2 header off, and I look at the layer 3 IP. If the destination IP address matches something that I have locally configured on one of my interfaces, whether it's a loopback or a physical interface of some type, then I know the packet was destined for me. If it doesn't match something that's configured locally, I then will call the routing process and say, okay, I need you guys to look in the routing table, look at the destination IP address, and say, okay, do you know how to deal with this? He looks at layer 3 IP, he consults the routing table or the routing information base, also commonly referred to as the RIB. He lets that traffic come in, the RIB looks at the traffic and says, okay, I do have a match in the routing table for that, which is great. And then the routing table says, okay, and in order to get there, you need to move the traffic towards this interface. It needs to go out that interface. So you're like, cool, all right, awesome. Next step in the process is you use the switching process inside of the router. There is a switching process in case you were not aware of that. The switching process moves the packet from the incoming interface to the outgoing interface. And at that point in time, that's when the layer 2 rewrite happens, when the layer 2 header is rewritten with the new source and destination MAC addresses, and it's forwarded on its way. That is how layer 3 vanilla routing works in a very, very high level nutshell, basic breakdown. I'm going to go through in a lot of detail and explain how that works later on. So don't worry about it if you don't understand that now, or if I confused you, that's okay. I have a dedicated video for that coming up soon, and that'll break that down. But I wanted to explain how the LLC comes into play, because a lot of times you're like, well, I don't get how you're going to have two different layers to the same, two different sub-layers to the same logical layer. How does that work? So MAC comes in, looks at the information, and it signals LLC to tell the layer 3 what to do with it. Now when it comes to standards, you have a couple different specifications. You've got .3U, which is going to be your 100 meg connections, .3Z, which is going to be your your gigabit over fiber. And you can run Ethernet over fiber, because fiber, at the end of the day, is just a physical media. It's whatever encapsulation you're running over that comes into play. And a lot of times you're going to have the right SFP to facilitate that. Like you might have SFP RJ45, where you know it's going to be an RJ45 jack plugging into that, or it might be an SFP LC to SC, things like that, which is going to be fiber optic cable, the physical fiber optic cable plugging into it. Because an SFP is just I'm trying to think of a good way to put it. It stands for small form factor pluggable, which basically it acts as like I want to say not a transistor, but it acts as a trying to think of a good word to use it. Basically, it comes in and it acts as a termination point for the cable. So you plug this in, you plug the the SFP module into the device in the appropriate port. You plug the cable into that module. The module itself is what translates between the cable traffic that's coming in off the cable to the device. So if you have fiber optic cabling, the fiber module will bring that fiber light in, or laser transmission into the module, and then it'll translate it over Ethernet or to an electrical signal. So basically it's a media translator and a media converter, for lack of a better term, and that is how you go about doing what you're going to do. The same thing can happen over twisted pair. So if you have an RJ45 jack, you plug it right into a gigabit interface on a router, you're good to go. You're running at gigabit speed. Now when it comes to CSMA CD, you're dealing with it breaks down. I broke this down on purpose so that it would be bullet pointed out. So you have your carrier sense, which is all devices on a common media. You have multiple access, which is multiple devices being able to communicate on the same common media. So basically a switch, right? So this is a layer 2 section. Makes sense to talk about switching. You have collision, which is 2 or more end stations try to send data at the same time. This was very common in hub world. Now, why is that a bit different than a switch? Well, a hub was basically just a layer 1 repeater. It would receive the electrical signals in on that cable, it would receive them in. It would not send those same electrical signals back out the same interface it received it on, because that would technically cause a loop. But what it would do is it would send that data out every interface on that hub, which meant that even devices that didn't need it or didn't care about it or it wasn't destined towards would receive that traffic. The problem with that being is if you don't have a way to have like a traffic control on your switch or on your hub, traffic was going to go everywhere all the time. Did not scale well. What was designed in the switch is what they call a MAC address table. The MAC address table would take the layer 2 information that was coming in on that device or on that port. It would look at the layer 2 information and say, okay, where are you trying to go? If the layer 2 header is this, then I place that MAC address in my MAC address table. You could affectionately call it layer 2 routing, because it would forward based off the destination MAC address. If it doesn't know the MAC address, it would go ahead and forward that information out every interface that's in that layer 2 broadcast domain, and then wait for a response to come back in. Wherever the response came from, it would know where to forward the traffic out of. The nice thing about it is whenever a computer would ARP, there's a thing known as gratuitous ARP, which basically is me walking into a room and saying, how's it going, everybody? My name's Rob, and we'll be hanging out for the rest of the series. You know who I am, but I don't know who any of you are, because you're watching this video and I don't get to see who's talking or who's watching the video. I have no idea. But you know who I am. That's okay, though, because if I'm going to put, and I'm located on gig 0/1, so you can reach Rob on gig 0/1. So if you have for instance, if you had a question for me, you would send your traffic towards me. You would put the destination MAC address as Rob, and then the switch would know, okay, in order to get to Rob, you need to go to gig 0/1, and then Rob will get the question. And then I would be able to respond to you, but then at that point in time, it's one-to-one communication between those ports, as long as they're in the same layer 2 network. If they're in different layer 2 networks, different broadcast domains, then we'd have to go through a layer 3 device, which could be that same box. There are switches that do layer 3 forwarding, or it could be a router, where the router you have to route towards the router would route back towards the destination network, and you go from there. I will go into that in much more detail later. You have collision detection. The data sent from 2 end stations collide on the wire. Well, that does happen. That's another hub aspect. Now, one of the things that most people don't realize about switches is when you're dealing with a switch, the switch has a CAM table, the content addressable memory table. This is where most of the memory for that switch is used. It's there in design, depending on how many MAC addresses are utilized, obviously. So you receive that information in, and what you do is you receive that information in and you save it. So for every MAC address that's been learned, has to sit in the CAM table. This is chewing up memory on the device, and what ends up happening here is let's say that the switch can handle a total of 200 MAC addresses. It's a very small switch, and you say, okay, cool. So what's going to end up happening is that traffic is going to come in on the switch, and then the moment that switch hits 200 MAC addresses, that it's learned in its MAC address table. What's going to end up happening for 201 and through any other MAC addresses it will learn, it won't know what to do with them, so it'll just start to broadcast everything. Because like, I don't want to drop your traffic, but I don't have anywhere to store your information, so I'm just going to send you everywhere. So what ends up happening is if a switch goes into, if it's CAM table, if its memory is all chewed up for learning MAC addresses, it turns into a hub. And then it starts advertising traffic every interface in that layer 2, in that VLAN essentially. So that's why switches or hubs were replaced with switches. And typically, I don't think I've ever been able to max out a switch's CAM table, especially newer switches. They can hold several thousand MAC addresses. And typically speaking, I don't ever like to push a big enough VLAN to where you might actually chew up 1,000 MAC addresses. Normally, I start to cut off between 200 and 300, and that's usually a /24. That's typically as big as I like to go, because then you're cutting down on the amount of chatter between devices and things like that. It makes things easier. So what happens when there is a collision? Well, when a collision is detected on the wire, known as the Jan signal, what ends up happening here is a random back timer is initiated, and both devices have to stop sending data. They can't send any data for that period of time. And then once they've done that, they have to wait for the all clear signal, which means they're listening on the wire, they don't hear anything. So they both think that they can send traffic at the same time. They go ahead and they are able to send traffic out on the interface, and if there's a collision, they both have to wait a little bit longer, but the backup timers are randomly set. I don't believe that there's any given set of time, but that's exactly how that would work out. Now, when it comes to Ethernet frame, you have the preamble, which the field consists of 7 bytes of alternating ones and zeros. It synchronizes the signals of communicating computers. You have the start of frame delimiter, or the soft delimiter. Transmission of actual frame is about to start, and that any data flowing is part of that packet. So it gives you like a, hey, so you know I'm on my way to you. And it's like you're calling ahead to let you know wherever you're going knows you're coming. The destination address is going to be the MAC address of the NIC where you're trying to go. So if you don't know what the destination MAC address is, you have to ARP for it, and then once the ARP reply comes back in, you're going to build a MAC address table with that. So beyond popular belief, there's actually a MAC address table on every computer that's on that LAN. So if you were to do go to the command prompt and do an ARP-A, you would see multiple MAC addresses on that computer, because it's built its own ARP cache. So that's how it knows how to get to something very, very quickly. The source address is the MAC of the sending computer. The ether type value, it typically indicates what the layer 3 packet will be, typically IP 0 by 800. There's a bunch of other ether type values. You're free to look them up at your own leisure. Data and pad. It's used to minimum length, let's see, if the data is too short, a string of extraneous bits is used to pad the field to its minimum length of 46 bytes. It is possible. I really wouldn't worry about that too much. And you have your frame check sequence, checking to make sure the data has not been corrupted. So that's the general breakdown to an FCS. So the FCSs are checked on both ends of the connection to make sure nothing happened. The same thing happens with OSPF updates and things like that. Ethernet MAC address. Components of a MAC address are pretty straightforward. It's split into 2 different segments. You have the first half, which is going to be your 24-bit OUI, or Organizational Unique Identifier. This is the manufacturer of the NIC. And there are going to be 2 bits in the very beginning of that, bit 1 and bit 2, that are, one is identified for multicast or broadcast, the other one is for locally administered address bit. I really wouldn't worry about that, just be aware that they're there. And if there's a 24-bit vendor assigned end station address, this is going to be the burned in address, or the BIA, that's actually applied to the MAC. Now on layer 3 devices, on routers and things like that, you can actually change the MAC address of the interface. I'm not going to do that, and I don't believe it's supported in Viral, but if it is, so be it. But just be aware you can change that. So like if you have a MAC address filter in your network where you're trying to filter out traffic from a particular MAC, you can change your MAC address, and then you can bypass a MAC filter. But there's a lot of things like you can get into things like 802.1x where you are only going to allow certain MAC addresses to go through, and if you change your MAC address, you'll lose connectivity. But that's a general breakdown to that. So that, in a nutshell, is how Ethernet works and some of the basics to it. We'll talk about that more and more as we get into demonstrations. You'll see exactly what that looks like.